Okay, let's think about where we were. We were right here. Now, one of the things that we're going to get into the habit of doing, it's not necessary, but once there starts to be lone pairs in your diagrams, just writing the negative can get lost, especially if you're sloppy. If you're a sloppy writer, and I can't tell whether that's a bond or a negative or just a dash, what is that? We're going to put our negatives and our positives into circles just to make them more obvious. That's not a rule. It's just a thing. Going to take these two electrons and make a covalent bond. Now, hand waving. Covalent bond is two electrons shared between two atoms. We have grown up understanding here's an electron unpaired, bonding electron. Here's an electron unpaired, another bonding electron. Two electrons shared between two atoms is a covalent bond. What if that non-bonding pair of electrons was responsible for both electrons in the bond? Still a covalent bond. This is what they used to call a dative bond, now called a coordinate, covalent or coordinative. Covalent bond. Still, two electrons shared between two atoms. So we've made a molecule out of an acid and out of the base. And this curved arrow notation, curved arrow means the motion of two electrons. There are lots of different types of arrow in the chemistry world. You already know a few of them. A straight arrow turns reactants into products. An arrow that goes forwards and backwards says this is a reversible reaction, and we would be expecting equilibrium in our reactant to product mix. This is motion of two electrons, and it comes from the base to the acid. Guess what this is? That's motion of one electron. Motion of two electrons, reactant to product, product to reactant. Okay, so you've got to be careful which arrow you use. When we're describing the flow of electrons in a reaction, we bend the arrows. Don't show me a straight line coming out of this and going to there. Don't do that. Bases make bonds. Acids, well, acids accept the bond. Remember what our definition of acids and bases was? That the Arrhenius definition and the Bronsted-Lowry definition for acids are not nearly as important in organic chemistry as the Lewis definition. And a Lewis acid was what? Electron pair acceptor. Not electron acceptor. Electron pair. They have to come in twos. There's your electron pair. The lone pair of electrons that the textbook in general chemistry foolishly wanted to call non-bonding is the thing that makes the bond between molecules. Okay, so the acid accepts a pair of electrons. The base has a pair of electrons to give. Take a second and think about of all of the chemicals that we're going to be faced with, where on the periodic table are the elements that are obviously going to be basic? Let me see if I can do this for you playing along at home. Nope. No, it doesn't spin around nearly far enough. Where on the periodic table are the bases? Yeah, we're going to just use the regular numbering system until we get to inorganic chemistry. Yeah, if you're in group 7, like a fluorine or a chlorine or a bromine, you only get to make one bond, but you have 3 lone pairs of electrons. If you want to be a base, you need to have a lone pair of electrons. What else?
Group 6.
How about if you're in group 6? Do the atoms in group 6 have lone pairs of electrons? People playing at home, yes or no? Yes, they do. Anywhere else on the periodic table that I might logically find an atom that is naturally predisposed to be a base?
5.
How about group 5?
Yes.
What's your favorite atom in group 5?
Okay. My favorite.
Nitrogen. Come on, people. All right, back to the book. How are we doing? Okay, so if you are a base, you make bonds. Specifically, bases make bonds to hydrogen. But our world of organic chemistry is going to be larger than just regular acid-base general chemistry. We're going to see the flow of electrons to atoms that are not hydrogen. We see flow of electrons to atoms that are carbon. So in general, anything that accepts a bond belongs to the family called electrophiles. Electro, electrons, phile, love. These things love electrons. Bases belong to the family of nucleophiles. So the nucleophile reaches out and grabs the electrophile. When we do get around to doing reactions, it's going to be a little while yet. We're going to force you to understand shape and structure before we get to reactions. But when we get to reactions, it's going to be reasonably simple. Reactions will do one of a couple of simple things. all reactions are basically going to fall into these categories. You're either going to add a molecule or a fragment onto a new molecule, to an existing molecule, to make a new molecule. You're going to perform a substitution where the incoming thing makes a better bond to the thing that this carbon was holding on to. And so for every new bond that you make, you lose an existing bond. Or you have an elimination, where you just lose something and you end up putting a double bond in there. So in the case of the additions, we're going to start with unsaturated molecules become saturated molecules. People at home, can you read this far to the right? No. In addition reactions, you take something that is unsaturated, like maybe an alkene, and you add something to it, and we take away double bonds and we end up with single bonds. In a substitution, you just replace. You replace a weak bond for a strong bond. And in an elimination, eliminations are the exact opposite of additions. We take something that is saturated and we make it unsaturated. That means giving up bonds. That means that this molecule, the reactant here, is going to share something in common with this molecule here. To do an elimination means you're also going to have something in your molecule that the bond is weak enough to break. So we're going to start building in areas of weakness into our molecules on purpose, so that we can remove them at a later date and replace them with things that we would rather have be there. Okay? All right. That's basically a preface to reaction chemistry that's coming a week from now. But before we get there, we have to look at three-dimensional shapes. I'm going to pan back so that we can read what's on the board. We've got a couple of things to talk about. First of which is configuration. Configuration is a map that tells us which atoms are attached to which other atoms. So if I were to look at something like C2H, what am I going to do? 6O. Go ahead and solve that. Draw me the calculate structure of C2H6O. Two carbons, 6 hydrogens, 1 oxygen. I'm going to start with the assumption that the carbons are bonded to each other. That leaves me 6 places left to bond if each carbon has 4 hydrogens, 4 bonds. So if I throw all the hydrogens on, I didn't put the oxygen in. The thing I know about oxygen, always makes 2 bonds, has 2 lone pairs of electrons. I just made ethanol. If the question on the test said, draw all the available calculate structures for C2H6O and name them, and you wrote this, you get half the points. What's missing? People playing at home, what have I missed? Come on now. Is that the only way that those atoms can combine? Oxygen always makes 2 bonds. Put the oxygen in the middle. Oxygen always makes 2 bonds. Put the oxygen in the middle. Carbon always makes 4. And Bob's your uncle. I've made something different. I've made something so fundamentally different that it's no longer an alcohol. Because alcohols have carbon to oxygen single bonds and then an oxygen to hydrogen single bond as well. This one doesn't. This has carbon to oxygen to carbon. This is different. It's an ether. These have different configuration. They're structural isomers in the way that in order to get from here to here, if you were using your little plastic model kits, and I brought some in for the people to use, and no one's touched them for months and months and months. So they're safe to handle today. We'll put them back in the box. We might even spray them with the disinfectant, and then they'll be good a week from now when you bring them out again. To get from here to here, I had to break the carbon to carbon bond, the oxygen to hydrogen bond, and then make a new bond. Detach the plastic pieces, reshuffle the places, and then put them back together again. That's a configuration. What we had been calling structural isomers are now configurational isomers or constitutional isomers. Multiple words all saying the same thing. Constitution, configuration, structure. We haven't learned how to name ethers yet. Ethers only have single bonds. Guess what the tail end of the word is if there's only single bonds? Ane. Ane means only single bonds. So we're going to name the longest chain ane, and then the whole substituent, including the oxygen. So this goes short chain, oxy, long chain, ane. So here's how I'm going to break this down. This and this are both the same length. Pick one. That's my substituent. This becomes methoxymethane. Ethers can be symmetrical or they can be asymmetric. When they're asymmetric, it's easier to name because there's clearly a small side and a big side. But the way that we make them most frequently in industry is in a process that generally makes them be symmetrical. So most of the ethers that you ever encounter are going to be symmetric. And the molecule that is called ether has an F here and an F there. It is ethoxyethane. And great smell. Don't smell the chemicals because it's a very, very powerful anesthetic and is also wickedly, wickedly flammable. So you smell it, you go unconscious, you leave the top off the bottle, then the room catches fire. Yeah, so don't smell the chemicals. This is configuration. Yeah.
Can you just reiterate how you differentiate between the short chain and the long chain in this one?
They're the same. Okay. They're the same. If it's the same name. It's the same name. These two are both the same length. One of them gets to be the long name of the chain. The other one gets to be the substituent. The oxygen has to find a way into the name some way, somehow. Let's have it be part of the substituent. So the substituent is what's inside the green box. Okay. All right. If you want to break out the plastic boxes, pass those back. Now then, to go along with configuration, we also have conformation. And conformation just tells us where are the bonds sitting in 3 dimensions. So, are we comfortable that this is butane? butane, right? Somebody make butane, plastic models. Somebody delegate or volunteer. These are both butane. But in my primitive two-dimensional representation, I think I'm trying to tell the reader something. It looks like I'm trying to tell the reader that in this molecule, all the carbons are laid out in a straight chain, whereas in this one, they're kind of in a zigzag. The configuration is not different. The configuration is this carbon is bonded to that carbon, is bonded to that carbon, is bonded to that one. Well, look, it's bonded to here, to here, to here, to here. So the arrangement of atoms, the bonding system is the same. What is different is these are three-dimensional molecules. There's 3 dimensions. Remember, what's the geometry here on this carbon? Somebody at home? Geometry of this carbon. It's tetrahedral. So that's taking up, so we would get sp3 is a valid answer right here too. It's taking up 3-dimensional space. We have a 2-dimensional representation. My 2-dimensional representation says that each of these bonds is 90 degrees, and that's nonsense. That's not true at all. They're not 90 degrees. What are they? 1 and 9.5. All right, I'm stretching because the molecule's not ready yet. Yeah, I know. So trying to convey that these are different. How are we doing?
Sure, you get the little light on the
Those wasn't as neatly subdivided as some of the other kids.
That's not true. You can tell.
Yeah.
Okay, and we're back. Oh, I do need one more hydrogen. Okay, so in 3 dimensions, if you pick the molecules up, and it depends, right? It depends what model kit you've got. But generally, if you pick the molecules up and give them a shake, they fall, gravity assists. They fall into the place that you would most likely find them in nature. And this, if I can fake it, is 4 carbons in a straight row. But it's not really straight. It's not really straight at all. Okay. This and this and this all have the same configuration. But this and this have different conformations. Conformations arise out of rotation. That's something that's not on the board yet, But now that we've made a molecule out of it, we can kind of see that. All right. This is an isolated carbon to hydrogen bond right here. If I rotate that bond, it has no consequence whatsoever. None at all. Because that's a little sphere. And when you rotate a sphere, you get a sphere. However, this carbon in the middle, between 1, 2, 3, 4, between carbons 2 and 3, if I rotate around that bond, oh, stuff happens. This is different than that. And it's different because where's the microphone? You might even be able to hear that at home. These atoms are touching. In this conformation. And what's on the outside of atoms? Electrons are on the outside of atoms. There's too many trick questions. You're not falling for the easy answers anymore. Electrons are on the outside of atoms, and electrons repel each other. So in this three-dimensional shape that is easily achievable just by rotation of this bond and by rotation of that bond, I got a boatload of repulsion here. Now I don't. Repulsion. Gone away. So I'm going to need to be able to show that in a way that is better than what I've got, because this isn't going to cut it. Conformation is the spatial arrangement of bonds in 3D. Can you see the end of the screen? Can you see the far right? Maybe not. How are we doing? I can always write small. Conformation changes via the rotation around single bonds. So, the first thing that we're going to do is draw representations of tetrahedra. Any bond that is in the plane of the paper is written as a straight line. Any bond that is pointing away from you is written as a hatched line. This is a hatch. This is a dash. This is not a dashed line. It is a hatched line. If you ever see a chemical bond that is drawn as a dash, that means that that bond is either just about to break or it's just about to be made. That's a bond that's not quite there. We're talking about hatched lines, not dashed lines. And if you are good enough, you can make them be a hatched wedge, because a wedge means that that bond is pointing towards you. So I've simplified my little molecule down to ethane. Here's ethane. And as 2 tetrahedra, it sits on 4 atoms. It's a little quadruped. It's a little dog with the head and the tail. It's happy, its tail's up. I can rotate these bonds between carbon number 1 and carbon number 2. If I rotate that bond, something happens to the energy. And the thing that's happening to the energy is there are electrons here and there are electrons there. At the point where the electrons are closest to each other during any rotation, energy is going to be the highest. At any point during the rotation, if I make this distance be larger, then my energy will drop. That distance right here is as close as they're ever going to be. And as I rotate, that distance is now as far as it's ever going to be. This representation is better than my previous representation, but it's still not complete. There is another way of showing this that shows the images, the detail better. And it's instead of looking at the molecule this way, side on, we're going to look at the molecule that way, head on, this way, head on. Not side on, head on. Now, I can see that this ball of electrons, it's actually in the bond, is right in front of the electrons that are behind it. And they're close. This is eclipsed. If I rotate the front, this distance has just increased, and they're not lined up right on top of each other anymore. They're staggered. But look what happens when I continue to rotate. Another atom takes its place. So as I do a full 360 rotation, I get areas of high repulsion, areas of low repulsion, areas of high repulsion, areas of low repulsion, areas of high repulsion. We're going to draw them this way as well. Okay. So let's look at what we've got. So here's my quadruped. If I rotate one of them so that the dog cocks its leg, it's now on 3 points. Draw that. We'll keep one of these the way that it is. Wedges mean pointing out towards you. Hatches mean pointing away. Here, for a very simple molecule, ethane, I have two conformations. They are called eclipsed and staggered. Okay, I'm going to convert what I've got on the board into something called a Newman projection. All right. This molecule sits on four legs with the head and the tail pointing up. If you're in the plane of the board, you're just a straight line. If you're pointing out towards you, you're a wedge. If you're pointing away, you're one of those hatched lines. Okay, so this is where we are. Going to turn the molecule directly at you and then sketch what we can see. I can see 3 hydrogens in an inverted Y. They're in an upside down Y shape or a Mercedes logo. I can see that they all converge at a central atom. Then I can't see the atoms that are behind them. If I kind of give a little bit of a tiny bit of a look, I can see that there's an atom behind and then other hydrogens, but they're eclipsed. This is in the way of that. That's what the eclipsed part means. So there's an atom at the back. And I know that the bond from this atom is going to that atom at the back. But I can't see the atom at the back because the atom at the front is in the way. Here's how we're going to represent that. That's the front part of my molecule. I can see 3 hydrogens coming to a point at the front of the molecule. And behind it, there's another atom. I'm going to draw a circle. That circle will not cross the lines of the existing bonds. It will not cross those lines because those lines are in front. That line is uninterrupted. This line is uninterrupted, and that line is uninterrupted because they're at the front and they're completely visible. And then behind is another bond from a hydrogen, and that bond goes to the outside of the circle. The circle represents the atom that is behind the front atom. So I have 3 bonds that go to the outside of the circle, and I have 3 bonds that meet at the center of the upside down Y. If I can see the atoms meet, that's the front. If I can't see where the atoms meet, that's the back. This is called a Newman projection. Let's do it for the staggered. So here was my eclipsed. if I rotate the atoms at the back, I get this. The front of the molecule is still the same. There are 3 atoms coming to a point. Behind it, there is another atom. I'm going to draw that as a circle, and then these bonds are going to go to that circle. This is an eclipsed human projection. This is a staggered human projection. Question. How much did I rotate a central carbon-carbon bond to make these hydrogens be as far apart as they're ever going to be? What is that angle?
60 degrees.
That's 60 degrees. In the eclipsed form, this is eclipsed. These electrons are repelling each other. As I twist away from it, they start to feel relief. Up to the point where this is as far apart as they're ever going. And then as they continue to rotate, they come back into being eclipsed again. This is the maximum that they can be apart. That angle is 60 degrees.
What's that little eyeball?
Oh, so to get from here to here, there's an eyeball, if you look in the notes, and it says, this is what we're doing. We're looking at this molecule right down the bond between the carbons, right here. So people playing at home, here's my molecule. It's eclipsed. I'm going to look straight down this bond. So my eyeball is here. I'm going to look straight down that bond. Here's what it looks like with my eyeball now here, looking straight down that bond. Okay. You've all done tremendously well. Take Monday off. And we'll see you on Wednesday. Wednesday, I will bring in a little piece of software on an iPad that's going to map these molecules and do the twisting and the conformation and make life so good. It's called iSpartan. It's about $20. Can't make you buy it. It's only on Apples, so whatever. But it is really, really useful. So we're going to do some of that. And then we're going to make these more difficult and twist them and look at what we've got. Okay? All right. Have a good weekend. Everybody stay safe. People at home, anything that you need from me? Yes, Marcel, it's called iSpartan. It's for iPhones and iPads. It's difficult to see on a phone. It's good on an iPad. It's helpful for a number of things. Really? I would have thought, well, okay. I wonder why it only has 3 stars. If you want to buy the PC software, it's about $3,000. The regular version of the software is $750. The student version is $50. The iPad app is $20.
What?
I know.
That's really dumb. I don't want to. Microsoft. You're telling me I'm paying $750?
No, because because you're a student, you would pay 50.
50.
Yeah, big student discount.
That's still a chunk of.
Yeah.
I'll do that though.
Okay, I'll see everybody on Wednesday. Keep an eye on Blackboard because there's probably a quiz, right?
Yeah. Sunday.
There's always a quiz.
Always good.